So welcome back. Now actually we are looking at this is a continuation of the previous video where we are going to actually look at a demonstration of what this really means about the basic trigonometric functions, or how one signal can be represented by a combination of signals. Okay, so I'm going to use this very nice tool that was built by controlsystemsacademy.com. I'm just using it, and all credit goes to them, and I'm really happy that I was able to find this tool. However, I'm going to use this to demonstrate what this idea is. Don't worry that you really don't understand if you don't understand what this means, because we are going to go into details of how do we decompose a signal into these Fourier coefficients. Okay, and remember we talked about a magnitude and a phase plot, so we'll go into details associated with that as well, but just this is a demonstration to show the basic idea behind it. All right, now here if you look here, we have a green. In green we have a square wave, and we can see that it is a periodic signal very clearly, right? And now we have a sinusoidal signal, pure sinusoidal signal. Okay, because we have the Fourier coefficients selected to be 1. Okay, and we know that in the frequency axis 0 means DC offset. There is no DC offset on this signal, therefore the DC component is 0. Alright, and we also know that there's a real and an imaginary component in the frequency domain for a pure sinusoid, and we can see that as well. Here, see, very nice, right? We can see all those, and then we can also see that there is a phase associated with it, and that clearly implies that this is a sine waveform. See, at t equals 0 the signal is 0, therefore it's a sine waveform. That's why there's a phase with a negative magnitude. Okay, so very nice tool. Now what we're going to do is we're going to try to build up a square wave using a series of sinusoids or pure harmonics. All right, now here we know that these two components with magnitude and phase builds up one sine wave. All right, but what is this individual component represent? Let's think about it. What does this individual component, let's forget about one of them. Let's forget this one. Let's forget this does not exist. Okay, and then what can we say about this component? How can we represent that mathematically? Okay, so if you answered using a complex exponential, then you are correct. All right, so this individual stem, we call them a stem, because in flowers you have a stem and a little, at the end you have a little bulge, so this is we call a stem. So using this one stem we show a complex exponential, and this is the negative complex exponential, and on the right hand side on the positive axis we have the positive complex exponential magnitude. All right, that's the magnitude component, the e j omega naught t component. All right, so we have that. Don't worry about the value here, 2 over pi. We'll learn more details about this later. Now, so here you can see we have a coefficient. Now let's add a second component. We have a second harmonic, we added one more, right? Second frequency component, and when you add one you have another one, because now we are adding second sine wave. All right, but the magnitude is 0. You learn why that is, so for now let's not worry about it. We add a third component. Oh, what happened now? So now with the third component we can see that our synthesized waveform got a little bit closer to our square wave, right? And that is with a third harmonic added, with a different magnitude. Okay, phase remain the same because obviously we are adding sinusoids, the phase does not change. All right, we add the fourth harmonic, that's 0. Okay, that's 0, that's fine. We add the fifth harmonic, it gets closer, even more closer than the previous signal. So we add a seventh harmonic, it gets closer, right? We add the ninth, 11th, 13th, 15th, right? So this tool stops at 15th. Now at 15th, it's almost like a square wave. Okay, so what this tells us is, by combining a series of sinusoids, we can represent a signal. If we have the ability to show infinite number of signals here, we can represent the exact square wave using this method. And this is the basic idea behind Fourier analysis or Fourier series. All right, now in our going forward, what we are going to learn here is, we are going to learn how do we find these magnitudes, because in real life you have no ability to visualize this without Fourier analysis. Okay, and what we are going to do is, we are going to come up with a technique that we can decompose our original signal, whether it's a square wave, a triangle wave, or a ramp, or whichever the signal is. We'll try to decompose it into the frequency components, negative side and the positive side, or alternatively sines and cosines, and we'll go talk about that in a little bit too. Okay, before I just close down this tool, let's look at a triangle, right? See, we have got closer, very close, but no sharp edges, right? So we are adding harmonics. See, it's getting closer and closer to our actual triangular waveform. Okay, very nice tool. Let's try again with a sawtooth. Okay, 2, so 3, 4, 5, 6. See, as we add, it gets closer and closer to our actual signal. How about a full wave rectified sine? Oh, see, very nice, very beautiful, right? So this Fourier analysis is a very beautiful, very unique technique. It has a lot of power to perform analysis on systems, understand underlying behavior, and develop control systems, and you're going to use it throughout your life. Okay, so very important that you understand it. So with that, I'm going to stop this video. You are welcome to go to the website and try out their tool and share your thoughts with me in class. Okay, so with that, we're going to stop or end the video